Hello, my name is Askara. Today I'm going to talk about calculus 3. And here is the subject that I picked is called directional derivative and gradient vector. Here is learning objective. We can determine the directional derivative in the direction of a function with two variables and using the gradient vector to calculate the given real value function and explain the significance of a gradient vector with regard to the direction of change along the surface and use the gradient to find the tangent level curve of a given function. Also, calculate the directional derivative and gradient in 3 dimensions. Take a look at the definition. The derivative of f(1) p sub 0, x sub 0, y sub 0 in the direction of unit vector u is equal to u1i plus u2j in is the number of ds over df over ds in the direction of u point p sub 0 is equal to limit of f x sub 0 plus s u plus s times u1 y sub 0 plus s times u2 minus f x sub 0 y sub 0 over s. Take a look at the example number 1 here. Find the derivative of y square plus find the sorry. Example number 1. Find the derivative of function y square plus x times y at point p sub 0 in the direction of unit vector u is equal to cos pi over 3i plus sin pi over 3j. And then by plugging the point 1 into this equation, we got 1 square plus 1 times 1 is equal to 2. And cos pi over 3 here is equal to 1 over 2, and sin pi over 3 here is equal to square root of 3 over 2. So by applying the definition, we got df over ds in the direction of u at point p sub 0 is equal to limit of f approaching 0 of f x sub 0 plus s times u1 y sub 0 plus s times u2 minus f1 1 over s. And then we got limit s approaches 0 f1 plus s over 2 1 plus s times square root 3 over 2 minus f1 1 over s. And then we got limit s approaches 0 of f1 plus s times square root 3 over 2 square plus 1 times 1 plus s over 2 times 1 plus s times square root 3 over 2 minus f1 1 over s. By the simplification this, we got limit s approaches 0 s times 3 times square root 3 over s times 3 times square root 3 plus 1 over 2 plus s times 3 over 4 plus square root 3 over 4 over s. This s and this s is cancel each other. The remaining answer here is 3 times square root 3 plus 1 over 2. So the rate of change of the function y square plus x and y at the point 1 1 in the direction u is 3 times square root 3 plus 1 over 2. Here the definition. The gradient vector of function of f of x and y at a point p sub 0, x sub 0, y sub 0 is the vector gradient vector is equal to partial derivative of x respect to x I plus partial derivative of f respect to yj. This is obtained by evaluating the partial derivative of f at point p sub 0. So the theorem 9, the directional derivative in a dot product is function of x and y is differentiable in an open region contain p sub 0, x sub 0, y sub 0, then df over ds in the direction u at point p sub 0 is equal to partial derivative is equal to the gradient at point p sub 0 times dot u. Here is the example number 2. Find the derivative of the function 2xy minus 3y square at point p sub 0 is 5y in the direction of u equal to 4i plus 3j. So the unit vector here is equal to 4i plus 3j over square root of 4 square plus 3 square equal to 4i over 5 plus 3 over 5j. So the gradient vector here is equal to partial derivative of f respect to xi plus partial derivative of f respect to yj. So the partial of function f at point 5 are given by partial derivative of y respect to x is equal to 2y partial derivative of y respect to partial derivative of f respect to y equal to 2x minus 6y. By plugging the point 5 into this equation, we got 10. Also, plugging the point 5 into this equation, we got minus 20 because here 2 times 5 is equal to 10, 6 times 5 is equal to 30, 10 minus 30 is equal to minus 20. And then the gradient vector at point 5 is equal to 10i minus 20j. And the directional derivative function of f in the direction of u at 0.55 is equal to the gradient vector at 0.55 dot unit vector u is equal to 10 times 3 over 4 minus 20 times 3 over 5 here is equal to minus 4. So the directional derivative here is equal to minus 4. And here is some property of the directional derivative. One, the function f decreases multiplicity when cos data is equal to 1 or when data is equal to 0, and u is the direction of the gradient vector. And that is an each point p in domain f increases multiplicity in direction of gradient vector at point p, and the derivative in this direction is the directional derivative of f in the direction of u is equal to absolute value of gradient vector times cos 0 is equal to absolute value of the gradient vector. Two, similarly of f decrease multiplicity in the direction of minus gradient vector, the direction is the derivative of the directional derivative of function of f in unit vector u is equal to absolute value of the gradient vector times cos pi is equal to minus absolute value of the gradient vector. 3, any direction u orthogonal to the gradient is not equal to 0 in a direction of zero change in f because data then equal to pi over 2, and the directional derivative of function f in the direction of u here is equal to absolute value the gradient vector times cos pi over 2 equal to the 0. And here is the example number 3. Find the direction which the function x squared plus xy plus y squared increase and decrease multiplicity at point minus 1, 1. Then find the derivative of the function in this picture. The partial derivative of f at point minus 1, 1 are given by the function x squared plus x times y plus y squared. So the partial derivative of f respect to x, here we got 2x plus y because this x equal to 2x and this is equal to y in respect to x, and in respect to y we got x here plus 2y here because this is equal to 0 in respect to y. So by plugging the point minus 1 and 1 into this equation, we got minus 1. Also plugging the minus 1 and 1 into this equation, we got 1. And the gradient vector at point minus 1, 1 is equal to minus I plus j. So the unit vector of the gradient is equal to the gradient vector over absolute value of the gradient vector. Here is equal to minus I plus j over square root of minus 1 square plus 1 square equal to minus 1 over square root of 2i plus 1 over square root of 2j. And f is increased multiplicity in the direction of u. Here is equal to minus 1 over 2i plus minus 1 plus 1 over 2j. And decrease multiplicity in the direction of minus u equal to 1 over 2i minus 1 over 2j. So the directional derivative of function of f in the direction of u at point p sub 0 equal to the gradient vector dot unit vector. We got minus I plus j times minus 1 over square root of 2i plus 1 over square root of 2j. A is equal to square root of 2. And it decrease, and the decreased one is equal to minus 2. Example number 4, find the equation of the tangent line x squared plus y squared equal to 4 at the point square root of 2 square root of 2. This is the so-called equation, and the gradient at point at point square root of 2 square root of 2 is equal to the, and we get the gradient vector here is equal to partial derivative of f respect to yi plus partial derivative of f respect to yj, and the gradient vector at point square root of 2 square root of 2 here is equal to 2i plus 2yj is equal to 2 times square root of 2i plus 2 times square root of 2j, because the partial derivative of f respect to here we got 2x this y is equal to 0 and 4 is equal to 0. The partial derivative of respect to y here is equal to 2yj because the x here is equal to 0 and the 4 here is equal to 0. So the tangent line equation here is equal to the partial derivative of respect to x at point x sub 0 y sub 0 times x minus x sub 0 plus y plus partial derivative of f respect to y at x minus sub 0 y sub 0 times y minus y sub 0 is equal to 0. So the tangent line here is equal to 2 times square root of 2 times x minus square root of 2 plus 2 times square root of 2 times y minus square root of 2 is equal to 0. And by simplifying this, we got square root of 2y plus square root of 2y here is equal to 4. And here are some algebra for the gradient. Number one is the sum rule. We can sum it by two functions, and the rest is still the same, right? This differential rule, contain multiply rule, product rule, and quotient rule. This is the last part, the function of three variable, and for the differentiable function of f by z and the unit vector u1i plus u2j plus u2k in space, we have the gradient vector equal to the partial derivative of f respect to xi plus the partial derivative of f respect to yj plus the partial derivative of f respect to k. And the directional unit vector function of f in the direction u is equal to the gradient vector dot u is equal to partial derivative of f respect to x u1 plus partial derivative of f respect to y times u2 plus partial derivative of y respect to z times u3. This is also the last example. Finding the derivative of the function x by plus y z plus x at p sub 0 is 1 minus 1 and 2. The directional of u is equal to 3i plus 6j minus 2k. The gradient of the gradient vector here is equal to partial derivative of f respect to xi plus partial derivative of f respect to y plus partial derivative of f respect to zk, and then we got partial derivative of f respect to x is equal to y plus z. Partial derivative of f respect to y is equal to x plus z. Partial derivative of z partial derivative of y respect to z is equal to x to y plus x. And by plugging the point 1 minus 1 and 2 into this equation, we got 1. Plugging this quantity of 0 into this equation, we got 3. Plus plugging p sub 0 here into this equation, we got 0. So the gradient vector here is equal to I plus 3j, and the unit vector here is equal to 3i plus 6j minus 2k over square root of 3 square plus 6 square plus 4 square here is equal to 3i over square root of 7 plus 6j over square root of 7 minus 2k over square root of 7. So the directional derivative of function f in the direction u upon p sub 0 here is equal to the gradient vector dot u vector. We got I plus 3j times 3i over square root of 7 plus 6j over square root of 7 minus 2k over square root of 7. So by simplifying this, we got 3. And this is all. And thank you for paying attention, and good luck.